So it's a great pleasure to introduce Marta Reina-Campos from McMaster to our seminar today a bit earlier than usual. Marta got her PhD from the University of Heidelberg in 2020, I think, and then moved or joined us here in Canada as a CITA National Fellow at McMaster and is coming here in fall. So Marta has been working on galaxy formation in general, and more specifically on star clusters in cosmological simulations a lot, both as dynamical tracers of the underlying matter distribution, but also their intrinsic properties, which is what she will be talking about today, I guess. Looking forward to your talk, so take it away.
Reiner, good morning, everyone. Can you all hear me well, especially on Zoom? Okay, well, if anyone complains on Zoom, please let me know and I'll try to be clear. Thanks, Reiner, for the nice introduction. As he said, I'm Marta. I'm currently at McMaster, which is like an hour away, so it's not too far. But starting this fall, I'll be here. And I'm interested on star clusters. I'm interested on them as tracers, as Reiner said, but I'm also interested on the star formation or how they form, what's their role as feedback sources, and how they evolve sort of over cosmic time within galaxies. And in order to study all of these processes, I've been using numerical simulations of galaxy formation, like the one that is playing in the background here, where you can see the gray color bar corresponds to the gas density. So here we have this filamentary structure that's sort of collapsing. This is the main galaxy. These are satellites. Each of these galaxies is forming its own stellar cluster populations, which are all of these dots that are running around, and they're color-coded by their metallicity. So blue are metal poor, red are metal rich. And you can see how using these simulations, we can study the formation and assembly of stellar cluster populations over cosmic time. So we can use the redshift zero properties and see if we reproduce what we see in the local universe and if we can make predictions for high redshift. In particular, for my talk today, I want to focus on these different topics. First, I want to sort of review what do we understand about star clusters in the local universe and what we're starting to see at high redshift. Then I'll describe how we can model star clusters within galaxies and all the assumptions that we have made for the EMP-Pathfinder simulations. And then I'll show some results in which we're trying to reproduce the masses and the half-mass radii of stellar clusters. And then I'll draft a couple of ideas that I have sort of going for the future. So starting with what are star clusters, I like to set everyone kind of on the same pace by going back kind of almost 200 or 300 years ago. To one of the first catalogs of star clusters and planetary nebula observed by William Herschel and his sister. And in those catalogs, they write that, but first of all, it will be necessary to explain what is our idea of a cluster of stars, and by what means we have obtained it. For an instance, I shall take the phenomenon which presents itself in many clusters. It is that of a number of lucid spots of equal luster scattered over a circular space, in such a manner as to appear gradually more compressed towards the middle, and which compression, in the clusters to which I allude, is generally carried so far as by imperceptible degrees to end in a luminous center of a resolvable blaze of light. We now know that the objects that William Herschel and his sister were observing are objects like these ones, where you can see a huge number of stars compressed in a really small region of space. And because of their sort of spherical shape, they were called globular clusters. If we look at the physical properties of these clusters, we now know that these are extremely massive and they're very bright objects. So they tend to have masses of the order of 10 to the 5 solar masses and higher. They're very old, at least the ones that we see in the Milky Way, with ages comparable to the age of the universe. So like kind of more than 10 years old. They're relatively metal poor, they're compact with half-mass radii of the order of 3 parsecs. And because you have so many stars in such a compact region of space, you would expect that all of these stars formed at once. But actually, when we're looking at the chemical abundances of the stars within these clusters, we're seeing that there's some scatter. So this is suggesting that there might have been several bursts of star formation within these compact regions. If we place these globular clusters in the context of the galaxy, this is a beautiful image of the Milky Way as seen by Gaia. This is a number density image where each pixel corresponds to the number of stars contained within the area covered by the pixel. And you might be able to see that there are some very bright spots sort of scattered around the galaxy. So we have the plane of the galaxy here with all the clouds of dust. We have the small and the large Magellanic clouds, and all of these bright spots. And
What's on top of that?
yes,
Just to the. Just on the left. Right there, that little dot.
oh, sorry.
Yeah, drop it.
So if you, yeah, exactly. There's one dot here. Sorry, didn't understand. Yeah, so if you identify all of these bright dots that we're sort of pointing at before, we actually see that these are kind of the globular clusters that were being observed by William Herschel and her sister. And you can see that there's plenty of them. Some of them seem to be sort of on the disk of the galaxy, but the vast majority of them seem to be sort of scattered around the galaxy, with many of them sitting in the halo. What's very interesting is that we see these sort of objects not just in the Milky Way, but in, so this is what like the clusters that we're looking at sort of look like. What's interesting is that we see these sort of very compact, super bright type of stellar objects, not just in the Milky Way, but basically in every galaxy we look at. So this figure is showing the total mass in globular clusters. And here by globular cluster, I mean sort of massive, old, sort of metal poor cluster. And I do this because every study defines it somewhat differently as a function of the halo mass that's hosting the galaxy in which they're residing. And you can see that here we're going from kind of 10 to the 6 to 10 to the 15 here. So just as a reference, this is what the SMC, Milky Way, the Fornax, and the Virgo clusters look like, are sitting. And you can see that in all of these different galactic environments, which are extremely different, they form and they assemble through very different mechanisms, we still see these massive gravitationally bound stellar systems. The only places where we are not sure whether we're seeing them is kind of in the dwarf regime, but that's probably related to the fact that these galaxies just don't have enough mass to form them, or they've never had enough gas to form these sort of clusters.
Globular clusters.
Understand this dark mass ratio.
Make up a significant fraction of the stellar mass if they were.
That's what's peculiar and will sort of come up later, is that we see that some of the dwarfs here have a significant fraction of their mass in globular clusters. So what we think might have happened is that these galaxies form, for example, through like one massive starburst, they form a few very massive clusters, and that's all. That was all the star formation within that galaxy. And then the fact that they have these clusters might have implications for how the galaxy evolved later on. So globular clusters, they're very interesting. We see them sort of everywhere, but actually we just focus on one galaxy and we focus on the Milky Way and its satellite galaxies. We see that the gravitationally bound stellar systems that we see are not just massive, they're not just metal poor, and they're not just old. This is a very nice figure from a recent review by McMaster and collaborators, in which they're showing different star clusters that we find in the Milky Way. So the Orion Nebulae cluster, which is currently forming, kind of up to 47 TAC, which is kind of older than 10 gigayears. And what we see in our own galaxy is that these star clusters, they have this huge range in ages, they have a huge range in metallicities, and also in masses. Some of them are like 100 solar masses. Some of these are like 10 to the 6 solar masses. So currently what we think is that star cluster formation is just a process, it's just a regular process in which the actual properties of star clusters just depend on where these clusters are forming and how they have evolved over time. And kind of within this idea, you would have that star clusters have just a distribution of properties, and globular clusters would just represent the extreme, massive, metal poor, and old end of this distribution. If this hypothesis were to be true, or sort of were to hold, you would expect that there should be young, massive cluster formation in the local universe if the gas conditions are right. And this is what we see when we observe highly starbursting environments. So this is just an image of an interacting galaxy. You can see the gray color bar corresponds to the gas density in the background. You can see that there's sort of a disk and there's this sort of tidal tail because it's an ongoing major merger. And all the color dots over here correspond to the stellar clusters that were observed in this system. And you can see that there's a lot of sort of young clusters, these are currently forming, and they're fairly massive. So the color goes from 10 to the 4, which is the vast majority, but there are also that are sort of, or the order of like 10 to the 6, 10 to the 7, which are sitting in the inner part. This is very interesting because it confirms this idea that like regular cluster formation seems to be capable of explaining the properties of star clusters that we see in galaxies. And there's been a lot of studies like using HST and focusing on doing this sort of analysis for starbursting systems in the local universe. What's very exciting these days is that James Webb is, of course, also revolutionizing this field. And by observing lens galaxies, like the one you have here, we can see these very bright spots, which are they're going to be massive and proto-globular clusters that they're forming. And this is very exciting because this is redshift 4. So these are sort of the time of the universe where we expect that most cluster formation happen. What's very exciting as well is that the properties that are being derived for these very bright clumps are the similar properties that we're seeing that are forming in these starbursting environments. So it seems to support the idea that massive cluster formation happens wherever there's a lot of star formation. And so you have a lot of gas pressure.
So just to be clear, we don't actually have evidence
The things we're seeing in that lensed galaxy are going to be bound, right? So
And that's a great point. So we see they're compact now. We cannot do, because these is still very limited, we cannot make dynamical studies about whether these are going to be bound or not. So what could happen is that they originally form as bound and they eventually dissolve. So that's something else that it's a problem when you're doing these sort of studies. So that's why these sort of objects are generally referred to as proto-globular clusters, because they form bound or they form massive and compact, and they may remain or may not.
Their title says early results, evidence for lens gravitationally bound proto-globular clusters. So they seem to be timing.
Yeah. The other idea out there sometimes being debated is, how can we know whether this is just one object or there's actually 3 and they are your resolution element? So whether this is like a 10 to yes. So why are also star clusters very relevant is because, as Matt Orr was explaining on Monday, star clusters can be prime feedback sources. So you have 10 to the 6 solar masses worth of stars in 3 parsecs. And all of those stars, because they form more or less at the same time, because they are expected to go supernovae and sort of eject all of their feedback more or less at the same time. So the amount of energy, momentum, and everything that you're sort of getting from these clusters, because they're clustered in space and time, it's going to be different than if all of that energy and momentum were to be distributed in the field. And this idea is relevant because we are now seeing objects like DF2, which is an ultra diffuse galaxy, that this is more or less what we see of the galaxy, and all of these bright dots are globular clusters. So this is one of the systems that you were referring to, where your globular cluster, your massive cluster population corresponds to most of the mass within your galaxy. So there's the idea, and this is something we explored a couple of years ago, that this galaxy forms through a starburst. It formed these stellar clusters, these very massive stellar clusters, and the feedback of these stellar clusters coupled to the dark matter potential and sort of broaden the potential, and that's why you see this very shallow structure. But they're interesting not just for the possible ramifications that it might have explaining the formation of UDGs. There's also the suggestion that we're now starting to see also with James Webb star clusters or proto-globular clusters in the sunrise arc, which is a galaxy supposed to be located at like redshift 6. So if we see these very bright objects and the energy ejected from these objects is capable of leaving the galaxy and sort of pouring outwards in the galaxy, they might also be sources for ionization. So this is an idea that has been in the field for a long time, and it's very exciting because now we can start sort of probing it observationally. So if we want to study how the stellar feedback from star clusters affects galaxies, we need to have a really good understanding of what are star clusters, how do they form, how do they evolve? And currently what we know is that cluster formation seems to depend on the natal environment. One of the properties that observers try to quantify is the efficiency to form bound star clusters. So if you see a galaxy and the galaxy is forming stars, what fraction of those stars are going to end up in gravitationally bound star clusters? And it's shown here as a function of the star formation rate surface density. And what we see is that in highly star bursting environments, most of your stellar mass forms in gravitationally bound clusters, which might or might not remain bound after these clusters form. But this is telling you that if those clusters were to go and do their feedback, they're going to do their feedback as tight knots rather than like as a dispersed field. The other quantity that observers try to quantify are the masses of these clusters. From a variety of studies, we seem to have converged to the idea that stellar clusters have masses that can be described by a Schechter function at birth. So this is a power law with a certain exponential truncation, and the mass at which this function truncates can be parameterized in terms of the gas surface density, the epicyclic frequency, and the Tumber parameter Q, which describes how stable a disk in hydrostatic equilibrium is to shear forces. What we see in observations is now we have this truncation mass here shown in the vertical axis, again as a function of the star formation rate surface density. And all of these color points are observations. What we see is that, again, in highly star bursting environments, not only you're forming most of your stellar mass in gravitationally bound star clusters, but these are going to be more massive. So in terms of feedback, you're going to get way more feedback from these clusters. So this is about how much mass you form and what masses they have. There are some other properties in which the environment doesn't seem to matter so much. So this is a figure from Brown and Gennett in 2021, where they took the 31 galaxies from the LEGO sample. This is an HST survey of star-forming spirals and dwarfs. They look at all the young star clusters, so clusters that are younger than 1 gigayear, and they systematically derive what is their size as a function of their masses. And you can see there's a huge scatter. And what's a bit annoying as a theorist is that there doesn't seem to be a reason for this scatter. So they look at these figures as a function of age of the clusters, as a function of the galaxy, as a function of the environment in which the clusters are sitting. And there didn't seem to be any kind of environmental variable that would explain why a 10 to the 4 cluster could have between 0.3 parsecs up to 10 parsecs. And this is a bit annoying because if you think again of the feedback that this sort of cluster can output, it's going to be much different, kind of the influence it's going to have if you are super compact than if you're much more extended. Now, these are kind of all the sort of formation properties or some of the formation properties that we normally look at when we're looking at star clusters. The other thing is what we were discussing, and is that after Hubble time, not all clusters survive. And the reason for this is that star clusters are a collection of stars, and one of the dominant disruption mechanisms, if not the main one, are tidal interactions with things that change the gravitational potential quickly. So the ones that are thought to dominate their lifetime are like you have a tidal shock with a passing GMC, and you can see that if you have your star cluster, there's a passing GMC sort of going back at the back of this cluster. And this is injecting kinetic energy into the stars of the cluster. And so they can become unbound and just sort of disperse. This disruption mechanism is extremely quick, and it's also very efficient at disrupting star clusters, especially in gas-rich environments. So while the star cluster is embedded in its natal gas environment, it's gonna suffer a lot of mass loss. The other disruption mechanism that's thought to dominate the amount of mass that star clusters lose, if the movie is playing, it's two-body relaxation. So within your cluster, you have a lot of stars that are sort of moving. If two stars exchange kinetic energy, one of them can sort of leave the cluster. And that's true for binaries, but also for other sort of multiple systems. This disruption mechanism has a longer time scale, and so it seems to dominate whatever there's not that much gas. But of course, these are just two things that are happening to star clusters. But in reality, there's like 1,000 different physical mechanisms that you can consider. There's also the fact that these are stars, so stars go through stellar evolution, and maybe the energy output of supernovae could also inject kinetic energy into the cluster. There's the thing that like massive star clusters undergo dynamical friction, and so in spiral into the galaxy. And if you want to get creative, there's also heating from the black hole population, or you have the formation of tidal tails. And all of these physical mechanisms are affecting the mass and also the size of star clusters. So if we now look at the evolved cluster populations, their mass distributions no longer follow a Schechter function, but they seem to follow a log normal. And this is telling us that most of the low mass clusters get eventually disrupted with time, and the massive ones seem to remain. So people have looked at what is the mean mass of the cluster mass function here in the vertical axis as a function of a stellar galaxy mass. You can see that this corresponds to a lot of different galactic environments, and this quantity seems to be fairly universal. So what this is telling us is the star clusters form with a wide variety of masses, but those that are especially low mass, they're going to get wiped out after a while. So if we go back to this kind of parameter space of size versus mass of star clusters, and we focus on the evolved star cluster populations, which are these diamonds and the blue dots. So this is M31 and the Milky Way. We see that preferentially 10 to the 5 solar mass cluster can survive 10 gigayears. And this explains why the object that William Herschel and his sister that they were observing were only the very massive kind of round globular clusters in the Milky Way. Do you have a question?
Explain to us what the most massive cluster will tell about the history of the galaxy.
They can tell you?
Well, I mean, M31 has a more massive cluster than the Milky Way.
Oh, that's a whole separate. No, that's all right. It's actually one of the reasons why these things are interesting on their own. They can tell you about the small scale physics when they form and they evolve, but you can also use them as traces of galaxy assembly. So there's a lot of people who have been looking at I've been looking at the position, but some other people have been looking at like the kinematics or the chemistry of star clusters and trying to relate how the galaxy form, how that connects. But I could give you more detail later. So we see that there are star clusters everywhere. They seem to have all sort of properties. So now how can we model them? How can we try and see whether we can reproduce their properties? So what we're trying to, just placing the problem in context, we need to be able to simulate starbursting environments like the Antony galaxies and the star cluster populations that are forming in them, down to quiescent environments like Cna, where we see that most of the cluster population is just sitting in the halo, while keeping into account that galaxies are not isolated, but they're actually connected with the cosmic web. So what we've done so in order to sort of solve this challenge, we've implemented our own galaxy formation model within a repo. And in this galaxy formation model, we include the multi-phase nature of the interstellar medium. So we're using a cooling network that is non-equilibrium from the Grackle library that allows us to simulate gas that goes down to 30 Kelvin. And this is going to be critical for modeling the star cluster populations, because at those low temperatures is where you get the giant molecular clouds that are going to drive most of star cluster disruption. And without the cold gas, you don't properly model the star clusters. Within our suite of galaxies, we decided to study how star formation happens. So we have a constant star formation efficiency, but also a turbulence-based prescription. And for the stellar feedback, we just focus on having mass, metals, energy, momentum from HGB winds, supernovae of type 2 and supernovae 1A. So kind of we eventually ran 25 simulations of cosmological zooming Milky Way mass galaxies, and we have 14 of them for the turbulence-based star formation. So this is just a pretty movie, which I hope it's playing well. So this is another view of how our galaxies are assembling. Now, the gas is not color-coded by density, but by the gas temperature. So you saw that at the beginning, all of the gas was cold, and it's the effect of the stellar feedback happening in the main galaxy, as well as in all the satellites that are sort of being accreted over time, what's heating up what would eventually become the CGM. While still having, anyway, so this is how we model galaxies. Now, how are we modeling the the stellar clusters? In order to be able to study star clusters over 13 gigayears, we have decided to use a subgrid prescription. And in this prescription, what we're doing is that for every gas particle that is eligible for star formation, all of our gas cells have 2 times 10 to the 5 solar masses. So this is way too large if we try to model the star clusters with individual particles. So every time we have a gas particle that should form a star, we calculate what is the kind of global gas surface density at the location of this cell, what is the epicyclic frequency and the Tumor parameter Q, and we let it form a star. Ta-da! Once we have the stellar particle, we assume some model. So we assume a model that describes what is the fraction of stars that should form gravitationally bound star clusters. We assume a model for what should be the maximum mass that the initial cluster mass function should have. And we make an assumption of what is going to be the initial size of these clusters. And with these three assumptions, we can sample a stellar cluster population that is going to live within the star. Once this stellar cluster population has formed, we have made other assumptions and we have other prescriptions that describe how the mass of these star clusters is changing over time and is being affected by tidal shocks, evaporation, dynamical friction, and stellar evolution. And we also have a prescription for how the size of these clusters is changing over time and is related to tidal shocks, evaporation, and stellar evolution. And with all of these assumptions, we have our stellar cluster populations and they can evolve over 13 gigayears. Something that's a caveat of this type of subgrid approximations, and that I like to be honest about, is that you have to be very careful because sometimes what you put in is what you put out. So sometimes the stellar cluster populations that you get at redshift 0 are very sensitive to these input models. So we have made an effort at trying to make sure that these prescriptions reproduce what we see in the local universe. So we hope they reproduce, once they evolve for 13 gigayears, they reproduce those star cluster populations. No, but it's very interesting. Just hold that idea. Because clusters are subgrid and they do nothing on the environment, we said, well, it's very expensive to run one simulation. So what if we have several star cluster populations within each of our galaxies? This allows us to study each of the different input models that we are assuming without changing the overall galactic environment. So we can really narrow down what is the effect of each of the different models. So within our fiducial galaxies, we have like a fiducial model. We can change the initial cluster mass. We can change what is the effect of tidal shocks onto the of the mass of the clusters and the initial cluster mass. We have different assumptions for the size and then sort of other changes on the formation of these clusters.
This is done in post-process.
No, this is at runtime.
So
So at runtime, when a bit of lag. So at runtime, when you make these assumptions and you sample the stellar clusters properties are just arrays within your stars. So rather than having one, you can have 10.
So do these star clusters feedback from the galaxy?
No, that's the reason.
Right,
So
that's why-
exactly. So the feedback is tied to the stellar particle properties and not to the star clusters. That's why we can make this game. Yeah. So we have these 10 populations. So why is it interesting to do these sort of simulations of star clusters in these cosmological environments? We cannot, I want to stress out, we cannot make predictions about the intrinsic cluster properties. We have no idea what's the profile of these clusters. We have no idea whether they're black holes. We have no idea of all of those sort of things.
If anything has been done in terms of you simulate a Milky Way or some galaxy, and then at some point you see a nice structure forming, and then you zoom in with the hydrodynamics. Is it possible to do that?
Yeah, I guess so. I know.
People are simulating regular cloud formation.
Yeah, so I know there's people.
Yeah.
Yeah, so I know there's also people at McMaster who are doing simulations of an isolated galaxy and having like different levels of like zoom in to focus onto one molecular cloud. Yes, that can be done. The problem those things have is you want to go to very high resolution, it's very expensive. So if you want to have stellar cluster populations over 13 gigayears, you have to compromise on something. And here we have compromised on resolution. So we're only, our particles are like 2 times 10 to the 5, and that kind of allows us to go. Otherwise, there's some people who have done it, so you're doing it. There's the people like McMaster, there are some other studies, but like you can model, you're more limited into what you can study. So the interesting thing for this talk, that you can do with these sort of simulations is that you can study the influence of the galactic environment on the cluster demographics. So are you getting the right masses, the sizes, metallicities, and so on? So let's look at that. So first of all, if I focus on the cluster masses, we can look at what is the mass function. So that here in the vertical axis, we have the number of globulars per mass bin as a function of the cluster mass. The green and the red lines are observed cluster mass functions for evolved systems. So the green is the Milky Way, the red is Milky Way and M31. The black line is the result of a previous study, which is called E-mosaics, where they're also using a galaxy formation model. In particular, they're using Eagle, and they couple it to similar subgrid description for star clusters. The main difference between Pathfinder and E-mosaics is that Eagle doesn't have cold gas. They only have warm gas, and then they have an equation of state. And their lack of cold gas means that they don't have sufficient tidal disruption, and they end up with too many low mass clusters. But what we see when we look at our simulations, and these are kind of the Redshift 0 results, these are the initial ones, is that because we have the cold gas, we have sufficient tidal shocks, such as properly reproduce the mass distributions of all globular clusters in the Milky Way and M31. So that was very interesting because it was a lot of work to do these simulations. We can look at the cluster.
Did you try the experiment? We run the simulation, but put it in temperature flow.
Claiming that it's the cold gas that does it. So that's how do you know that? All you've done is you've done a simulation which has cold gas in it, and you get this result.
We did turn on the tidal shock.
Oh, did you just turn up tidal shocking?
Did I turn on what?
Well-
In series of comparisons, one of them said no tidal shock. That one.
I don't remember doing that. Might be. So what we see is, so what we're seeing is that because we have cold gas, the density distribution of your gas, it's much denser and it's much clumpier. And that's driving much sort of spikier tidal shocks in your tidal history.
Did look at the
Did look at that. Yeah.
potential.
Yeah, we did look at that when we were doing our.
So the other way to test it, as I say, is just to turn off the cooling, leave the gas warm. See if you reproduce the other result.
Yeah.
Exactly.
That would be the other one.
It'd be too expensive.
It shouldn't be, because I guess if you don't have, I mean, the main reason why ours, yeah, so the main reason, yeah, so the main reason why ours is because they end up being very cold and very dense. So yeah, that would be easier. Yeah, we didn't thought of that, but it could have been something else that we could have done. So we looked at the masses sort of briefly. We seem to get what we see in the Milky Way. We also did a bit of a brief study at the metallicity, so just the content of iron in these clusters, and we're within the range of the observed distributions, although ours seem to be much more kind of unimodal and peak at like higher metallicities.
How does doing that? How does mixing work
within a repo, because it's, you know, it's Lagrangian, and so you might have some issues with.
I mean, it is Lagrangian, but there is phase mixing, like there is mixing between the phases, right? Reiner might know better.
Yeah, the mixing is numerical,
But it's sufficient to mix up the gas.
who knows exactly. But theoretically, like you would be able to incorporate a diffusion term if you really wanted to. I think some people have.
Well, fire has another fusion to put in.
Yeah.
Just for that.
Yeah. And so the last property we sort of briefly looked at is just where are these clusters sitting within the galaxy? And this is the number density radial profile. These are Milky Way and M31, sort of look what you would expect. So that was really interesting. Now a disclaimer, I said we have 10 different cluster populations. These are the results for when we are assuming, it is our fiducial kind of setup, which is we're assuming a constant cluster half mass radio of 4 parsec, and this radio doesn't change with time. So this is wrong, because this is wrong. This is simple and simplistic. And this is not what we see in the local universe. So we thought, okay, what happens if you change the initial sizes? So I took one of our galaxies and I remade the 10 different models that we were looking at. That's the nice thing of this framework. You can just fix everything and change one input model. And so you can do very controlled experiments of what's the influence of that particular model. So in this case, we're just changing what is the initial size of clusters. And now we have 10 different permutations. All clusters have the same size, which is unrealistic, but it's simple, it's nice. We like nice things. So this is the fiducial one that we had earlier. This is a model in which the initial size depends on the natal gas conditions of the cluster. Now we're assuming constant density with a scatter, and the next 6 models are the fits that were performed onto the Lagos galaxies at whether you're looking at very young star clusters, so 1 to 10 mega years without scatter, with scatter as a 2D histogram, and the 10 to 100 mega year. So when you take this galaxy and all of these different models and you sort of let it evolve for 13 giga years, what you get is something like this. So now I'm comparing it to the observed star clusters in M83, M31, and the Milky Way. These are the color dots that are sort of here. In this case, clusters start with a size, and that size doesn't change. So clusters cannot move up and down. They can only move towards the left in this diagram. And that's why we see that in the models where there was no initial scatter, you get a bit of scatter because kind of all your clusters are sort of drifting towards that. What we see is that it's still unrealistic because we expect that the size of star clusters is going to change with time. Some of our models seem to agree fairly well with observations, but we're missing these very extended star clusters up here. So we said, okay, let's now switch on the size evolution model. What does it happen? Ta-da, everything is the same. So this was not great. Some of the models still seem to, well, most of them are reproducing sort of these clusters. Some of them are also reproducing the more compact ones, but we're still missing these extended objects. The reason why the initial conditions sort of get erased over 13 giga years is because we're using a very simplistic differential equation to describe how the size should evolve. So this is the way we are changing the size. This is saying that the change in size is a term that depends on how much mass your cluster is losing due to tidal shocks, and a term that says how much mass your cluster is losing because of evaporation. And because the vast majority of clusters lose most of their mass because of shocks, this term is dominating, and that's why everything sort of collapses in the same way in this parameter space. What's happening in this differential equation is that if you have tidal shocks, that is contracting your clusters. And if you have evaporation and stellar evolution, that is expanding your clusters. So depending on which disruption mechanism is dominating over the lifetime of the clusters, that's affecting how the size is evolving over time. What we found is that this differential equation makes clusters to move into like a safe region of parameter space, where eventually neither of these disruption mechanisms produces much mass loss, and that's why clusters can survive with time. So we looked at what were the kind of the final properties of these different models. And here I'm showing the mass function as a function of the mass of the cluster. The top row corresponds to the galaxy where the size remains constant. The second one is if the size evolves with time. All of these different sort of bluish, greenish lines correspond to the different models that we're assuming for the initial size of the cluster. These 3 lines, the pink, orange, and red, correspond to the observed stellar cluster populations. So if the size doesn't change, the young ones have mass functions that are what we see in the local universe. This is a bit this is a bit of the input model that we're putting in, so we shouldn't trust this panel too much. But after 6 giga years of evolution, our mass distributions are peaked more or less similarly to what we see in the M31, although some of them have too many compact low mass clusters. And if we go at 10 giga years, unfortunately, the only model or one of the few models that seem to reproduce the mass distribution are those that have no scatter, which is unphysical or it's unrealistic. So that's a bit of a shame. If we have size evolution on, all of the models then start behaving the same, and we have too many low mass clusters because they have moved into this region of parameter space that is safe, and so they're not losing much mass because of shocks or evaporation. We can also look at the size distribution. So now is the number of clusters per kind of being in size.
You're moving into this regime where there's not a lot of evolution, but this is also at lower mass, right? So wouldn't that speed up you said that relaxation wasn't important, but wouldn't that speed up the two-body relaxation?
Yes, but we don't see that. So what we see is that the low mass clusters end up being very compact, like very, very, very compact. And so, yes, it would speed up two-body relaxation, but not sufficiently, because it seems to have still a longer time scale than what you would need to disrupt these clusters.
Two-body relaxation time is the dynamical time times what, n over log n, something like that.
Could you say again?
Two-body relaxation time is the dynamical time times n over log n, I think. So if you make the cluster more compact, that accelerates the two-body relaxation, doesn't it? Or
Yes, so that's what you would expect, but we're not saying it, or at least what we're saying is that in the balance between shocks and evaporation might be faster, but shock seems to be as well, or at least they seem to be kind of balancing them out. We have done runs with, so we have done runs where both of these are affecting the mass evolution, but only one of them the size. And indeed, the shape that we were seeing in the size mass relation was because of the shocks. So shocks are so much more efficient at driving mass loss than evaporation that just, it's wiping out whatever signature you might have from evaporation and from the initial size mass. So when we're looking at the size distribution now, so this is the number of clusters per bin of size as a function of the half mass radii. Young clusters seem to more or less reproduce what we see in M83. Now, if the size doesn't change, we see too many compact clusters in the kind of intermediate and old ages, and we see this sort of tail of extended clusters that we're not reproducing. We think these tail are weird objects in the Milky Way. So there are some clusters in the Milky Way that are specially puffed up. They have tidal tails, those sort of things, which we do not have in our model. So that's why we think this is expected, that we're not reproducing these objects. And if we make the size evolve, everything ends up being the same. So what this leads us is to the idea that simulated star cluster populations seem to be very sensitive, not just to the initial size mass relation that you're assuming, but also at whether you're letting the size evolve. So this is a problem because we need to make sure that the input models that we're assuming in these simulations are trustable and that our results are not going to depend too much on them. So how can we move forward? This is a bit of my rambling on this topic. So feel free to interrupt if you have other ideas. So what I think some of the things that we can do is, well, just keep on working on these equations and try to make them better. So I've said that the way we're evolving the sizes is a term that depends on the mass loss of shocks, a term that depends on the mass loss of evaporation. And this term means that tidal shocks are only contracting clusters, but this is not what we see. We see that tidal shocks can also expand star clusters. And in fact, if clusters are massive and very dense, what you expect from shocks is at first, rather than them losing mass, they're going to puff up until they fill their tidal radius, and then they're going to start losing mass. That is still not incorporated in this term, so that might change the answer somewhat. And then there's the idea that you might have some mass loss independent terms that might be modifying your size, so you could potentially work out those terms and improve this size, this sort of size evolution equation. It's challenging. There's not that many people that want to work on this. I've asked several people that have published previous paper on the topic whether they would be willing on exploring other aspects, and they were like, no, this is too difficult. So unfortunately, this doesn't seem to be something that people are kind of interested in. Something else that can be done is say, well, using subgrid descriptions is it has some limitations because you're limited by the resolution, you're limited by the input models that you're using in the simulation. So let's go the other way. Let's go crazy and let's try and resolve everything in the simulation. So there are some people who are doing extremely high resolution simulations. This one in particular has 4 solar masses and 0.1 parsecs of gravitational softening of dwarf galaxies. This is very impressive. They're putting in individual So they're resolving the IMF, they're putting in stellar feedback that depends on the individual stellar particles, and they can produce very realistic type of dwarf. They're doing very impressive work. The problem is because you're going to have such high resolutions, you can only evolve your systems for a few hundred mega years. So you can draw some conclusions, but you cannot make the entire connection with the early universe as we would like to do. So these, so the line group, they're using SPH-GAL, which is a branch of Gadget 3. There's some other people, so Thales Gatke, she also had some papers where she was using a REPL. And then, yeah, there are the approaches that you and Chris are doing of like zooming in. There's also other work that is being done at McMaster. So this seems to be one way that the field has decided to go, but it has its limitations because you're trying to achieve super high resolution. Especially if you really want to resolve the clusters, you not only need to resolve the masses, but you also need to resolve the gravitational interactions of the stars within the cluster. And for that, you like 0.1 parsecs is still too large. You would need to go to like AU so that you can do proper binaries and proper multiples. But that's really difficult at the moment. So the other approach that the community seems to be doing is try something different. Rather than assuming that your stellar clusters are subgrid within your stars, let's use what's called a sync algorithm. And syncs are very interesting because everyone uses them for something different. So a sync is a numerical method in which rather than having instantaneous star formation in your simulation, so say within the same time step, you have one gas cell, hey, you have a star. What you do is that you have a gas cell. If that gas cell becomes dense, it's in a convergent flow, whichever criteria you want, it turns into a sync. This sync can accrete gas, and in some cases, it can also merge with other objects. So there's the idea of merging of syncs, merging of clusters. This approach is typically used to reproduce or to model black holes. It's also starting to be used to model like individual stars within like cloud simulations, and it's also being used in some cases to model star clusters. So there's been several papers coming out from Oleg Genedin's group at Michigan in which they're doing high resolution simulations that are cosmological of local groups, and they're using art. The problem they have is that because they're trying, their syncs are creating within a certain radii, that radii is said to be 5 parsecs. So they need the refinement of the cell to be smaller than that. That imposes a very strong requirement on the resolution. And because they're trying to do cosmological runs, it means that they can only run up to like Redshift 2, Redshift 4 was the latest paper. So they can do a lot of studying kind of the early universe conditions, but it's very difficult to kind of compare to what's happening at Redshift 0. There are some other groups that are using syncs in Ramses, and they're doing like high resolution isolated simulations of Milky Way mass galaxies. In this case, they're not really interested in the cluster. I was actually kind of going through the paper trying to find what are the masses. So this figure is showing the gray color bar corresponds to the gas density, and all of the dots are their syncs, which are scaled by the mass and also color coded by the mass. You can see how some of the syncs are very small, they haven't accreted much mass, but some of them are very large. I was trying to see what small and large meant, but I couldn't find the numbers in their paper. So this is very interesting. They're doing this with Ramses, but these things can only accrete gas. So they don't have the idea of merging of clusters that you were suggesting, which is critical because in high resolution simulations of clouds, we're seeing that massive clusters build via a combination of in situ star formation and hierarchical merging. So these processes seem to be relevant if you want to model massive cluster formation, which is what I'm trying to do. But life is complicated and I didn't manage to make a figure in time. So stay tuned for next year's CITA seminar, and hopefully I have some more results on this aspect. Thank you for your attention. And I'm happy to take any questions.
I mean, how long do the syncs last?
So that's a good question. In principle, if feedback is efficient, creation of gas shouldn't last for long. If feedback is efficient. So the work, I'm not sure about these ones. I know they had to they had to impose a time scale to say if you're still accreting after 15 mega years, I think it was, you have to stop. because their feedback wasn't efficient enough. It might have been because they were using art and they had some trouble with that. So that's one of the things that hopefully, so we're working with Gizmo. I've been implementing all the feedback prescriptions so that they can work with syncs, so that the syncs can accrete and they can merge between them. And in principle, if feedback is sufficiently strong, we don't need to have to sort of hard criteria.
So in your half mass radii distribution plots, I'm curious what those very puffy clusters are in the Milky Way.
Yeah.
Yeah, they don't look very massive. They're like 10 to the 4, 10 to the 5, and then they're kind of puffy. I don't know if they're like, do they have any distinct properties, or do they like core collapse?
I think we looked at some of these clusters. We think these are the ones that are close to dissolution. So these are the clusters that are, as you say, they're not very massive. They're sort of 10 to the 14-ish solar masses. They're very extended. Some of them have tidal tails. So we think that these clusters have moved up in this diagram because they're dissolving. And so they are sort of puffing up and they're developing these tidal tails, and eventually everything will become unbound and you no longer will have a cluster.
Okay.
In our simulations is that we don't have that mechanism. We don't have that prescription. So that's why we're like, our clusters are not moving in that direction.
Where are they in the Milky Way?
I don't know, but we have a list of the clusters in the paper. I can let you know the identifiers later.
Questions? I have plenty. So if you would take your history of like one of those clusters in your simulation with all the shocks and encounters and whatnot, and run an n-body simulation, like an explicit n-body simulations for the kind of modeling these effects, would you trust to get the same result?
No. No. I mean, ideally, it would be great if they would agree, because the mass loss prescriptions we're using, they're tuned to n-body simulations. But to go from an n-body simulation onto differential equations that you can then plug into these things, you need to make assumptions. So one of the models we had in our kind of suite of simulations, let me try and find it. So yeah, so this model in particular, it's using a different prescription for the mass loss from the tidal shocks. This is a prescription that comes directly from n-body simulations, where we have one star cluster, we inject one shock, and we say, okay, what is the mass loss? But that shock only happens in one component of the tidal tensor, and it is extensive. So you are always puffing up your cluster, so you're always going to have mass loss. What happens if the shock is compressive and you have two consecutive shocks? So you have one compression and a second compression. How is the mass loss from that? We don't know. It's very challenging to model these things. So ideally, yes, they would agree. In reality, I'm sure there would be differences.
Okay, other questions online or?
Just following up on that, you know the tidal potential for all your clusters for the entire run, at least in principle. You could just do what Reina was suggesting, just take an n-body simulation and subject it to that tidal field.
Yeah, absolutely. So, I mean, we can do it. We can do the experiment. Actually, I'm going to be working with Jeremy Webb down over there. He has been asking me for the tidal histories of some of these objects because he wants to train neural networks and see if instead of doing n-body simulations, some of these processes could be simplified. So, and we're also working on a project where we're trying to say, okay, if you describe the ISM as or the tidal histories of the ISM as a power spectrum, and you draw tidal histories from that power spectrum, are the are the mass loss histories that clusters undergo self-similar? So can you describe them? Those are ideas that are being explored at the moment.
You showed at the beginning some clusters in a dwarf galaxy. I'm wondering, if you go to a dwarf galaxy, do you have preservation of the cluster distribution because the tidal environment is less, you know, shocky?
I mean, it is now. It might not have been when the clusters form, right? You still need a lot of gas to form those clusters. So even in the brief instant where those clusters were forming, they might have undergone a lot of tidal shocking. And then, yeah, there may be evaporation, and then the gas might sort of go away, and then you just have evaporation.
So what does it,
I haven't looked at dwarfs in particular, but that's something that I would expect.
that could be related to the observation that you have apparently more stars and clusters versus the field? Because, you know, if you don't disrupt clusters, then that's,
Yeah, that might be something else. Yeah, you're just not disrupting them. Yeah. We're very efficient at forming them. We're very efficient at forming them, and yeah. Yeah.
So I guess since the clusters are forming with the galaxy, there's no like repeating tidal shocks when the clusters go through the galactic disk and then like.
So the clusters form with the galaxy, but then they move away. So the clusters, so here I'm just showing the ones that are old, and this is just a projection. But you can see kind of in other visualizations of the galaxy that clusters form wherever you have a lot of gas, and they combine in the universe. We expect that the combined effect of the feedback from the clusters and the high rate of mergers at high redshift is forcing the clusters to migrate from the disk onto the halo. And because they can, and then they would sort of start undergoing this shocking. And because they migrate from these environments, that's what might explain why they survive. Because if they were to remain in the disk where there's a lot of tidal shocking, you would disappear. But they go, they're sort of safe, and then they just lose mass whenever they shock the disk.
Yeah, like that. Okay, so your simulations include like this effect. Okay.
We model the tidal shocks. We don't assume anything for the perturber. We're just looking at how is the gravitational potential changing at runtime. Is it gas? Is it disk shocking? Is it another star that's passing by? We don't know. We're sort of agnostic in that sense. But anything that changes the potential and quick enough produces a shock.
Okay, yeah, sorry, just one last question. Does your galaxy at the end look like Milky Way, for example?
In what aspect? Because we know a lot of things on the Milky Way.
No.
Stellar mass, yes, they do. In sort of overall properties, they seem to look like. So these galaxies were chosen to be, they had similar halo masses to the Milky Way, and they come from the high resolution volume of Eagle, which had 25 of these objects, and we sort of rerun some of them. So the only reason why we say it's Milky Way is because they have the same halo mass, but
Okay.
no criteria on morphology or merger history or anything else.
Okay, since it is noon already, let's thank Marta again.
Yes.